Hello. Uh, so this session is an extension to the first session, or maybe it has a different kind of approach. It's a holistic approach to seeing the Postgres-XC as a shared nothing cluster system. Did you guys, any of you attended yesterday's Postgres-XC session? No? Okay. So the agenda is, briefly we will go through the architecture of Postgres-XC and then go through the different aspects of, different essentials of a shared nothing cluster system and how it applies to Postgres-XC. And in the end, we will go through the different features which Postgres-XC supports in terms of the PostgreSQL features and the future directions. So first of all, let's go through what's the user view, what's the applications, do the applications require any changes, the current existing PostgreSQL applications, do they need to be aware of the cluster system? The answer is no. Whatever applications we have for PostgreSQL should work. They work on just by replacing the PostgreSQL server with the PostgreSQL-XC. So what lies beneath the PostgreSQL-XC server? So the client, the PG client connects to a server which is called Postgres-XC coordinator, and beneath that there are a number of nodes, as you can see, number of machines. The Postgres-XC coordinator connects to different nodes which are called data nodes. The data nodes are the ones which have the data. The coordinators doesn't have user data. So this is all transparent to the user applications. And all the nodes are connected with each other. The data nodes and the coordinators are connected with each other using a libpq interface. And so basically you can see here that we don't have any shared stuff. This is all of the data is distributed. Each of these servers are their standalone servers. All of the servers are Postgres-XC standalone servers. So in short, this is what is a shared nothing cluster system. Each of these servers have their own memory, have their own machines, their own CPUs, and their own data which is distributed. The data nodes are not aware of any other data nodes. The connection is only from the coordinator to the data nodes. And additionally, we can have multiple coordinators and multiple clients connecting to different coordinators at the same time. And all of these clients have a consistent view of the database, regardless of which coordinators they are connected to. And at the same time, this is a synchronous view. I mean, there is no lag of any data visibility, whether it connects to any of the coordinators. So if we are saying everything is non-shared, everything is, all of those nodes have their own memory, own disks. There should be some way to the shared memory stuff in PostgreSQL, the shared memory has some data which is shared. So what's the data? The data is the transaction ID, the snapshots. So because we don't have a shared memory here, the memory is also independent of all the nodes. That's the reason we need the snapshot, we need the transaction ID, and those transaction IDs should be unique to the whole cluster system. For that purpose, we have something called as GTM. GTM is again a standalone server which is not based on PostgreSQL server. It's a standalone process running on maybe on another machine. But this is the one which supplies the global transaction IDs and the snapshots. So the snapshot contains a list of transaction IDs. In PostgreSQL, we have those IDs, but what we want here is we want the transaction IDs to have the scope of the whole cluster. So those snapshots are the transaction IDs are global. So the list of transaction IDs in the snapshot should be fetched from a central location, that is GTM. So let's go through the pros and cons of a shared nothing cluster and see how it gets applied to PostgreSQL-XC and what it does, how it handles all of these. So when we talk about shared nothing cluster, the obvious part, the one part which is the primary benefit of this is the scalability and performance. Why is it? Because there is no sharing of CPU, no disk sharing, and no memory sharing. So there is no question of a bottleneck here. And second point is lower hardware cost. All of these servers are, because they are PostgreSQL servers, they don't require any special hardware. They can just run on a commodity hardware. Third one is about, because we have multiple nodes, multiple servers, obviously what we want is high availability from, we don't want a single point of failures. And actually there is a scope of data redundancy because there are multiple nodes running the same part of the cluster. So we can very well do the data redundancy and exploit the high availability part. But at the same time, even though we have these benefits, there are some points which a DBA has to be careful about. When we are talking about shared nothing cluster, there is always data which is spread out to different locations, and the coordinator is coordinator is at one location and the data is on another location. So obviously there is going to be fetching of that data and data movement, and that is not present in a shared disk system because it's in the same location. But here we have data spread out. So this will have to, the shared nothing cluster system has to take care of this. And the Postgres-XC doesn't run without any modifications. It has to do a lot of awareness of the cluster system. It has to be aware of the cluster system and have to implement different logic to fetch the data and handle the distributed data. It doesn't come automatically. So we need an effort to implement this kind of system. And third one is that because there are a lot of nodes, lot of machines in the cluster system, obviously we want to manage those nodes. So the management of nodes, addition of nodes, removal of nodes requires reorganizing the data. So let's see how Postgres-XC handles all of these points. So first of all, about scalability. When we talk about scalability, of course we want scalability. That scalability is the main primary reason why people want to go to a shared nothing cluster system, right? So, but to achieve scalability, there are a lot of factors which a DBA needs to be careful about. First thing is why scalability comes. The main thing is parallelism, because there are multiple CPUs, multiple different disks on different locations. Nothing is shared. So obviously we should have some parallelism in that. Load balancing. I mean, if we just spread out nodes and start to pile up data and there is no load balancing, obviously the parallelism part gets affected. So there are some factors which actually can hamper the performance if you don't take care of it. Data distribution, which is again, the half of the work is about data distribution. Additional to the optimizations in the Postgres-XC cluster system, there are tasks for a DBA to do. You cannot ignore this. If the data distribution is not right, there is no use of whatever performance optimizations are done inside the implementation. And the data movement. So let's go through it one by one. First of all, let's know what actually Postgres-XC is doing about it. So Postgres-XC has two types of table distributions. One is we can distribute the data. The table can be a distributed table, or else it can be a replicated table. So it can be either distributed or replicated, not both. So how is it distributed? First, at the create table time, we have to specify whether it's distributed or not. And by default, it is created as a distributed table, or you can explicitly say on which nodes we want to distribute the data. Nodes in the sense data nodes here. So from the coordinator, when we insert into a coordinator, into a table which is distributed, transparently it goes and distributes to the specified nodes, and it actually depends on what type of distribution we have. So here the insert is actually it knows that we want to insert into which data node transparently. So basically distributed tables are okay for updations, for point updations, like I will come to that. So here is an example of a select query where it wants to fetch data depending on a single where clause, a basic where clause, where it wants to retrieve data from a row which is ID equal to 3. So because the table is distributed according to hash, it knows that ID equal to 3 lies into a particular node, so it will only fetch through that data node. It won't involve any other data node. Similarly, update. All the select and update queries which are point queries will go into one particular data node. This is how distributed tables are good. I mean, if you specify a particular value for fetching a where clause, it knows which data node it wants to go to. So the distributed tables can be distributed using different mechanisms. Hash involves getting a hash value of a particular value and then deciding which data node we want to insert into. Modulo is, it divides that value by the number of nodes. Distribute by round robin means it keeps on rotating the data nodes into which it inserts the values. So round robin is beneficial if you have more inserts. It's not beneficial if we have a select or a update. What we haven't yet supported is distribute by range, which is like you give a particular range of values which will go into only one particular data node. That we don't yet support. And we don't yet support vertical fragmentation, that is divide the data according to a different columns, a set of columns going into one data node and other set of columns going into another data node. About replicated tables, basically it replicates the data to a particular set of nodes. So again, at the create table time, we need to specify that this table needs to be replicated on a set of data nodes. So this insert query, basically the insert queries will always act on multiple data nodes. So replicated tables is not good if we have lot of modifications, lot of updates and inserts, because it will have to do it on each of these nodes. But for selects, the coordinator has a choice of from which data node to select. So here we have a select star from employee, and the table is replicated on D1 and D3, and it has a choice to either retrieve it from D1 or D3, and how it chooses. One way is to specify something called as preferred node for each coordinator. So here, if we specify that D3 is a preferred node for C1, so this configuration, it will take advantage of this, and the query will only retrieve from D3. Basically, this preferred nodes helps in distributing the load. So suppose there are multiple queries on the same table. Some of those queries, one from one coordinator and other queries from the other coordinator. Each coordinator has their own preferred nodes. So these queries will go to different data nodes, and that's how we achieve parallelism. So this is one example configuration. We have multiple coordinators, multiple data nodes, multiple clients connecting to the two coordinators. Here we have one replicated table, which is replicated on D2 and D3. And D2 is a preferred node of C1, and D3 is a preferred node of C2. Why we have done this? Because in this case, D2 data node and C1 are on the same machine, and D3 and C2 are again on one common machine. So we want this to be preferred because if we basically to reduce the data movement from the coordinator to the data nodes. And a select star from a replicated table from coordinator C1 will go to D2, and from C2 it will go to D3. So they are completely parallel in true sense. They are using their own CPU, their own disks. There is no sharing of, these queries don't go to the same machine, they go to a different machine. And at the same time, the update employee goes to another data node. There also it has found out that this query should be executed on one particular data node, not on multiple data nodes, because it knows that the ID equal to 100 value is always going to be on data node 1. So this is one configuration which we generally do, the setting of preferred nodes and keeping the preferred data node on the same machine as the coordinator. This is what we actually have done when we have executed the DBT1 performance test. And it really helps. So about parallelism, we talked about parallelism, but where all is the parallelism in the cluster? Okay, one location where we can do is, which we have seen here in the earlier slides, is that multiple queries are actually running in parallel on different CPUs. But what about the Postgres-XC internals? The Postgres-XC internals. Does Postgres-XC handle any parallel, explicitly any parallel stuff? So there is one area which it actually runs, it runs parallel queries on data nodes. That part is when we want to do a table scan on a table, distributed table. We actually fetch those values from different data nodes in parallel. Though the plan node is one plan node, the table scan node, but it actually fetches those the data rows from multiple data nodes. Other than that, Postgres-XC doesn't do any parallel stuff. We can, in the future, there is a lot of scope to increase the parallelism inside the Postgres-XC system transparently. One potential part where we can do is we can the join table, the tables which are involved in the join. The vanilla PostgreSQL doesn't have any way to execute the join tables in parallel, fetch those results in parallel, the scans in parallel. So that's the area where we can actually benefits in Postgres-XC, because there's no point in sequentially fetching, waiting for the results to come from one table and then fetching the results from another table from the data nodes. We can do it in parallel, asynchronously. Load balancing. Like we saw just now, the replicated tables are a very good option for load balancing, for reading data, because the coordinator has a choice from where to read. We have seen the preferred nodes for replicated tables, where the DBA can specify from which data nodes to fetch the tables. Additionally, Postgres-XC randomly chooses the data node from which to fetch if there is no preferred node. So this actually achieves randomness, and that's how we achieve load balancing. We don't want all the coordinators to fetch the results only from one data node. We want to balance out, and that's what it actually happens because of the randomness of choosing a data node. And of course, data distribution. Data distribution is a very important in terms of load balancing also. If we don't do it correctly, if we keep on distributing data only on one particular set of data nodes, and some data nodes get idle, there's no point of doing that, because we have 10 data nodes and we only distribute it on some particular data nodes, and there is very less data, or basically data distribution is all connected to load balancing. And what we can achieve in the future, we don't have actually any support of coordinator level load balancing. So the coordinator itself also has some work to do. Coordinator can process rows, and it has to involve, it does get involved in processing of rows. And if we don't, if the coordinator gets a lot of load, we want to have some external mechanism which can distribute the client requests to different coordinators. But that is a thing which can be done by some third-party tool. Postgres-XC doesn't have anything for that. So we talked briefly about the data movement. So in this particular example, okay, there are two where conditions in this select, okay, and the request sent to the coordinator is delegated to the data nodes. And what we don't want here is, we don't want all of the data to be fetched from data nodes to the coordinator. There is already a where clause which is saying it wants to fetch only particular set of rows. And if we don't handle it correctly, we don't want to, suppose the table has thousands of rows and the actual selectivity is very less and the client only wants 3 rows. And still if we fetch all of those rows from the data node to coordinator, really we don't want to do that. But what do we do for that? So the coordinator is able to figure out which all where clause conditions it can actually delegate to the data node. So here it pushes down the where clause which it can. In this case, it's ID equal to 3. It knows that it can generate a query for the data node to be executed on, and it supplies the where clause there. But it doesn't do it for the other condition. The other condition is old employee. So somehow it figures out that that function is not good to be run on the data nodes. So what essentially is happening here is it's not very much ideal. It cannot completely prevent the data movement here, because the is old employee where condition is going to be applied on the coordinator. So it will have to fetch some more rows from data node to coordinator, and then handle the where clause at the coordinator. So something about the explain plan outputs in case of Postgres-XC. So this is the same query which we talked about. How does it look in PostgreSQL? This is the typical PostgreSQL which you might be, this format of explain output you might be aware of. It's a sequential scan, and it shows the filter of 2 conditions, employee ID equal to 3 and the function call. In Postgres-XC, we have a data node scan instead of a table scan. So that is corresponding to the sequential scan here. And it shows that which all data nodes it went and fetched those results from. And it also shows the remote query it ran on the data nodes. And plus it shows the calls which are applied on the coordinator, not on the data node. So we can see that the where clause in the query has been gone into the data nodes, but the other where clause call has been applied on coordinators. So there are ways to figure out things only by using explain output. So what all gets pushed to the data nodes? The coordinator's task is to figure out what all tasks to delegate to the data nodes and get rid of itself doing the work. So immutable functions are one example. because we know that the immutable function has the same return value regardless of anything else, it knows that it's safe to be executed on data nodes. So it will push that function call to the data node. Constant expressions and joins which involve at least one common replicated table. So joins are a big thing to work on. Like, we really don't want the join tables whole data to be fetched from the data nodes to the coordinators and the coordinator doing all of the stuff. So if it knows that it's able to push down the join onto the data nodes, it will reduce the data movement a lot. And how it can figure it out? It knows that a replicated table, if the two tables are replicated on one common on one common node, data node, it can execute the whole join on only one particular data node. And in ideal case, it can completely ship the query. That's called fast query shipping. It can completely ship the query and doesn't have to worry about anything. It will just, the coordinator will just act as a proxy. It will just route those fetched results back to the client. So there are a lot of things to do right now. There are a lot of other things to make this efficient. There's a lot of development being going on here. So we have taken a join example here. So how to figure out whether this explain is actually showing us that this is good, this query is good. We are actually reducing the data movement. So the thumb rules are that anything other than the data node, okay, is happening on coordinator. So this, I have run this query on a coordinator, and the plan is actually being prepared on the coordinator. So whatever nodes we see, hash join, this is happening on coordinator, right? So we don't want that. So if we find this explain output, this is not good because the join is happening on the coordinator. That means it has to fetch all of the data. These two data nodes which it shows, it's fetching the whole data from the data nodes. Any questions so far? Okay. So what we want to do here is, the DBA typically what he should do is try to figure out why this is happening, why hasn't it done the join on the data node. Maybe the two tables are on different tables, it's not distributed, it's not replicated, and if it's not replicated, it can't delegate to one particular node. So maybe we can, instead of the distributed tables, we want it on a replicated tables. How much read queries are being executed on these tables? Are they really, are there a lot of inserts and updates on these tables? If there are inserts and updates on this table, lot of inserts, we don't want it to be replicated because replicated tables are not good for table updates. So this is a join query. Are there a lot of join queries, lot of read queries on this? Then yes, we want it to be replicated. The employee and department table, are there a lot of joins happening? If there are a lot of joins happening and if there are a lot of read queries, we do want these two tables to be replicated on the same particular set of nodes. If we do that, we can see a different plan. So the same query, now what it does is, it says it's a single data node scan. It's a single data node scan, and it calls it as a remote SQS query because it's a fast query shipping query. It has shipped the whole query to one particular data node. So if you see that the number of data nodes is only one here. data node 1. It has determined that the data node 1 has all that information, all the data which it needs. So it will just ship the whole query. So here we have found out that there is no processing involved in coordinator. The parent node itself is a data node scan. There are no other nodes. That means there is nothing going on in the coordinator. The coordinator will only just route the data which it has got from the data node back to the client. Cost estimates. Basically, we don't have any cost estimation. We don't use any cost estimation. There is a lot of scope for future work, but basically, we don't consider any. Don't have any cluster awareness in terms of calculating the costs of maybe data transfer from the data nodes. We don't have any statistics on the coordinator. So the analyze command doesn't work. There's no use running analyze, except that it will do it on the data nodes also. So the data nodes have costs of their own. They are just like, they are basically PostgreSQL like servers running, standalone servers. So all of the cost estimation and plans do happen on data nodes, but not on the coordinators. Coordinator cannot estimate the cost and cannot choose a good plan, but it can choose which data node to delegate and other things, other XC stuff things, but it cannot do the path, the right choice of paths. So suppose we have different joint table paths. It's not possible to actually judge which path is good because it doesn't have any costs. So the cheapest path cannot be chosen. What about deadlocks? So because we are dealing here with multiple nodes at different standalone multiple nodes, there is a need of awareness of this possibility of deadlock in the whole cluster. So when we talk about deadlocks in PG also we have a possibility of a deadlock, but it's aware of it and it is able to determine the deadlocks and it returns an error. So suppose there are two different rows being updated by two different sessions, but their order of updation is different. So one process has a lock on one row, and another process has a lock on a different row. And after that, they start asking for each other's rows, and they have a deadlock here. So PG identifies this and returns an error. But this is a single node in case of Postgres-XC. We want to be aware of a different, if the two rows are on a different data nodes, we don't handle it. So there is a possibility of deadlocks in such cases. And there is another possibility of having a deadlock in case of replicated tables, which we actually do handle it. There is something called a primary data node. Basically, if there is a choice of, a table has been replicated to two data nodes, and one query locks one data node, and another query has a lock on a different data node, and then they afterwards they try to get lock on each other's data nodes. That's the problem of deadlocks even for a single data row. So it makes sure that they lock only one particular data node first, so that the serialization can occur here. That's the reason we have the assignment of primary data node So each coordinator should assign a fixed primary data node. They should not be different, so that it actually goes and executes the update on that particular data node first, so that the serialization can occur. Maybe we can, I think we are going to remove this requirement of assigning a primary data node but as of now we cannot do that unless we assign the primary data node. So we are talking about a lot of scalability stuff, and do we actually compromise the ACID properties in doing that? Let's look at that. So as I talked about the GTM stuff, when we talk about different nodes accessing different data rows, different data, there should not be a visibility problem. All the nodes, all the queries should have a consistent view of the same database. And what we do is, like I talked about, we have a GTM stuff, central location from where we get this unique global GXID. And addition to that, the GTM also is used for getting a couple of other data, like a timestamp, a global timestamp, and a sequence number, a unique sequence number. It's not a local. It's when we handle sequences, it's fetched from GTM. Otherwise, if we have all those unique snapshots, the MECC takes care of that, so we don't need to bother about the consistency. We have some restrictions on global constraints. Postgres-XC doesn't bother to check the constraints on a different data node. Suppose there is a unique key constraint, and it tries to insert one value on a data node. It knows that that value cannot be on another data node because it's a unique key. But suppose the unique key is not on a distributed column, then it has to actually go to the other data node to check whether that value is already there on the other data node, which Postgres-XC doesn't do that. So what Postgres-XC has done is, when we specify a unique key or any unique key constraints while creating the table, we actually disallow these such type of unique key constraints on columns which are not distributed. So we don't allow such scenarios to occur at the creation of the table itself. Basically, the attempt to create table with a constraint that requires to do that constraint check to other data nodes, that is not allowed. Maybe in the future we can support the global constraints, but as of now we don't do it. And another result is we cannot also update a distribution key, because if we update the distribution key, it might the new value may be applicable to other data node, not this data node. So we don't do that. We don't support updating a distribution key. Transaction isolation. So we do support the read committed and repeatable read, but the serializable transaction isolation, we fall back to repeatable read. So we don't support the serializable snapshot isolation globally in the cluster level. And for atomicity, we do support the two-phase protocol. So the two-phase protocol is actually required because there are multiple data nodes which do the write for the same query, and there are chances of one of the data nodes returning an abort, and other data nodes is actually trying to do a commit. And the typical scenario for two-phase protocol requires all the data nodes to either commit or abort. So whenever, and the coordinator actually is the one who initiates the two-phase protocol. And for efficiency, we don't use the two-phase protocol if the nodes involved in the write are just a single node. So, and of course, if the application explicitly asks for prepare transaction, then again we use the two-phase protocol. So for that, if there are temp tables, the temporary tables involved, in the PG we don't support two-phase protocol involved in the temp tables. So if we want to use temp tables in XC and those tables happen to be distributed to different nodes, then we have to set this enforce two-phase commit to off. This is always off in case of PG, but for XC, it's by default it's on, so we have to set it off. And other than the snapshot and GXID, we also have the commit log, but the commit log is actually used for maybe recovery, but the commit log is okay to be separate for individual data nodes. It doesn't have to be a unique globally unique commit log. Each data nodes have their own data commit log. So what happens if actually some of the nodes crash after prepare transaction but before abort or commit? So in this case, the crash node has that transaction in a prepared transaction mode. So for that we have to, once we recover that node, we have to specify what to do about that. So for that purpose, which we have PG-XC clean utility, which will clean up such transactions. First, we can see what all transactions are in such mode by using this PG prepared exacts table. It will show such kind of transactions. So basically, PG-XC clean will just issue commit prepared for such transactions. Bottlenecks. Do we have bottlenecks in XC cluster? Yes, we actually do have them. One is when the GTM is a central component, just a single component on a different machine, which is the only one where this information about the snapshot is there. So all the nodes will keep on fetching those snapshots and the GXID from the GTM. And once there are a lot of simultaneous requests, simultaneous queries, there are huge amount of requests to the GTM, just a single component. And plus, when there are a lot of simultaneous transactions, the list of transaction IDs in the snapshot goes on increasing. So the snapshot itself goes on increasing. So the amount of memory, amount of data requests is more, and the requests themselves are more. So GTM is overloaded. So that's the bottleneck here. So for that purpose, what we have done is we have something called as GTM proxy on each of the coordinators. So GTM proxy is local to the coordinator, whereas GTM is on a different location. What GTM proxy does is it merges different requests, simultaneous requests, into one request and considers these requests actually at the same time, to be actually at the same time, and then propagates that request as just a single request to GTM. Another area where this kind of stuff can happen is a coordinator has lot of requests from the clients, and it has to, for each request, it has to uh, send a query to the data nodes, and for each query, each different requests, it has to spawn the backend process on data nodes. So if there are thousands of requests, it will keep on spawning different backends on data nodes. So transparent to the user, whereas transparent to the user, there is a puller process which actually DBA doesn't have to uh, take care of much. It happens quite transparently. So there is a puller process between the coordinator and the data node. And the puller process uh, is actually there on the machine where the coordinator is there. So each coordinator has a puller process for each of the data nodes and for each of the remote coordinators also. So typical puller is a typical puller which keeps a number of backend connections open, so it doesn't close them off. It reuses those connections. It doesn't exit from those connections, and the coordinator requests the puller to fetch the data, and the data goes through the puller and comes back to the coordinator. High availability. So like I talked before, high availability there is a scope for improving the high availability without any external requirement, any external infrastructure, because we have a scope of redundancy of data on different data nodes. But right now we don't do it. There is no way to have high availability, like complete failover stuff, without requiring any external mechanism. Uh, there is, in one scenario, if the replicated table has, if the data node fails and there aren't any requests to the data node, still the cluster keeps on running. But if there is a request on that data node, that queries don't work. And if the node has all the replicated data and there are other nodes which have the same data, if one of the data node crashes, there is no current automatic failover to the other data node. So that's why we don't have any inbuilt HA stuff. There's a lot of scope to do that, however. So we just do this using the PG replication stuff. For each data node, we need to do all of this. And even for the GTM stuff, we want to do this. GTM standby is what we do for, it's corresponding to the slave node. But for automatic failover, we actually require some middleware, HA middleware called as pacemaker. Okay, I might have to wrap up a bit fast. So using pacemaker, actually we can do the automatic failover, but there is a lot of research work going on, a lot of work going on. The Linux HA Japan team is actually working on it. The recovery stuff, again, we have to be, the cluster has to be aware of the complete cluster. So we have something called as barrier ID, create barrier ID, which is run by any coordinator, and it actually creates a recovery point, which can be given in the time of recovery. So recovery.conf can have this barrier ID, and we can recover up till a consistent point in the whole cluster. Catalog objects, there are different, basically catalog objects are local to the coordinators and the data nodes. We cannot, it's not like if the query has the query has catalog tables, it will just run on the local nodes. Triggers, we actually are implementing right now. They are not supported right now. User functions are defined in all the nodes. This is just a brief cluster initialization. We just run the create node on all the coordinators. Each of these nodes have their own mode of running, data node or coordinator. Cluster management, we don't have any online node removal or online node addition. We don't do that. Right now it's just a static create node. Initially, we cannot do the online node removal addition. And we have a way to redistribute the data table wise. Okay, so you can, this is again, I think we are short of time for the feature support. So there are a lot of scope for the future improvements, save points, query processing improvements, online node addition. Okay, that's it. We have the mailing lists, of course. Okay, that's it on my side. Any questions? Okay, thank you.